Somebody want to grab a coffee? You're going to talk on this?
Yes. Nico, this is the thing. Sí, ojalá menos. Mucho de positivo.
Just to ask her.
She said it already.
Oh, I didn't see. So she just keep it.
Okay, so hello everybody for the first day of our workshop. Okay, I want to make one announcement about, so if you need a certificate, or if you want a certificate for participation and or giving a talk, then you just send me an email. And today we have our first talks by Gustavo, and it's a collaboration with Soham, and it's about quantum description of some model with a lot of ends. So please,
Thank you. Thank you to all for coming and attending this talk. Okay, in this occasion, I'm going to talk about this project with my postdoc advisor, Soham Biswas. So the idea is to present some preliminary ideas and results about this project because, to be honest, we exactly don't know how to proceed, but to study these kind of models using some approaches that we had previously. But this is the thing. We are going to do a try, some ideas, and we hope you can give us some feedback about that. And that will be nice. Okay, let me just present the outline. We have a motivation, a target systems, quantum extension approach, previous work, the model we want to study right now, and some preliminary results or ideas. Okay, what is the motivation for us? The thing is that we focus our approach in the sense that, or in the rule that small things create big changes in the world. So in the same way, like the hobbitses changed the destiny of the whole Middle Earth, small creatures, but doing great things. So we think that quantum effects, even if they survive in some kind of systems, and these quantum effects are very small, apparently insignificant, they can create or they can produce big changes in some observables. So this is the idea, the motivation of this kind of of works. Then, for example, when you work with many body complex systems, in principle, you can study, for example, one molecule, study all its properties and characteristics, and you think that everything is understood. But when you put many of these pieces together and start to interact each other or with some forces, external forces, then appear some rich collective phenomena or effects that are very interesting and very important to analyze. One example is, for example, the superradiance. When you put many atoms or molecules that can absorb one, then re-emit that photon, maybe in a different frequency, but when they start very close together, they start interact with the electromagnetic field, all these molecules synchronize to emit at the same time. So this phenomenon is called superradiance. See, instead that every molecule emit its photon randomly, they put they together synchronize to emit the photon at the same time. Other uh, applications of these collective phenomena is uh, the energy transfer in some molecules. The molecules absorbs, for example, one photon, and then for some reason this energy needs to move another location of a big molecule. So many things should happen that in the middle, so this event can happen, this energy transfer. So in a molecule, it's a big system, very complex system that interact with a lot of things. So a lot of synchronization in the electronical degrees of freedom of the molecule, also in the vibronic mode, need to be happen in such a way that the photon that is absorbed in one location is transferred to another location. For whatever reason that is necessary, these things could happen. I'm going to show you a few examples later. What kind of system we are interested in? We are interested in systems that, in some sense, contains or can accept quantum effects or quantum properties, but there is a lot of noise in the system. For example, now in the area of the quantum computing, that is called NIS, noisy intermediate scale quantum, work with a big quantum processor with many qubits. The interaction between these qubits introduce noise. Also, the environment, if you don't protect carefully the uh, the quantum CPU, is affected a lot about the the noise from the environment of the many parties that are interacting. So certainly this is a quantum systems that has a lot of properties that we are looking for a quantum computer, but when you scale or you try to scale, there are a lot of noisy participants, see, in the systems, such a way that the quantum effects are washed out, don't disappear, but are very washed out or diminished. Other kind of system, for example, that uh, um, has this kind of behavior is, for example, uh, the complex recollectors of light, for example, in algae or plants. They absorb light from the sun. It's absorbed by this kind of, ¿cómo se dice? Oleas? This kind of slides or antennas, see, but the light is not transformed in chemical energy in this position. The photons should be moved to the reaction center. Then when one photon is absorbed, if you simulate the path that this photon can follow, for example, with a random walk, this process is very inefficient. So then the idea is that some quantum should happen in this kind of system, such a way that when the photon is absorbed, it's transferred to efficient way. See? And apparently, the way that explain this efficient process is when you introduce quantum effects. These quantum effects are measured, are being measured in laboratories. For example, this very famous paper that firstly measured these quantum effects in kind of systems like this. Again, many things should happen in the middle for this process to be performed. Many collective phenomena should appear here, not just the electronic degrees of freedom of the system participate, the vibronic modes from the whole molecule, see, also participate such a way that the energy from the photon is transferred to the reaction center, and many other things also, because this is a system that is directly interacting with the environment at room temperature and something like that, right? So these are very, very complex systems. So many interesting collective phenomena appear in this system, such a way process like energy transfer could be realized in a very efficient way. So other examples are the superradiance I already mentioned, when you have a lot of molecules that can absorb light. So I'll put, for example, in these microtubule systems, then when one photon is absorbed, this photon is absorbed by the whole system in a kind of superposition or entangled state. And then this state is a metastable state that actually dissipate the energy of the photon, but do it in a way, in a collective way, like this. For example, this microtubule is radiating at the same time many molecules at the same time, and this is it's called a superradiant state. A difference from this case when the only a few molecules are emitting the photon to the outside. So this is just a few examples. These are a few examples of these kind of systems that typically contains quantum effects, but these quantum effects are very small because these systems interact with the environment, and the environment are, for example, these kind of system microtubules live in the cytoskeleton of the cells and the neurons. You know, the cytoskeleton is what maintains the shape of the neuron. So they are very important. Why these systems in these biological systems has these quantum properties? Nobody knows, but we found that these quantum properties are there. So they are very small, but they are very important for some kind of physical process in these biological systems. Okay, our approach to study systems that are very noisy, but they still contain some quantum effects, it's called, or we call it quantum extensions, and it was published previously in this PRE paper, and consists basically in the following. We studied a classical stochastic process that contain a finite sample space and are discrete in time. In such a way, you can prepare your system, your classical in a vector of probabilities, where every Q here corresponds to the probability that some of configurations of the systems. For example, if you have n coins and you want to throw out it, you can find that this is the probability that all coins get a head, one coin tail, or the rest head, etc. Right? So the initial state is prepared in this probability vector with these conditions should be fulfilled. Then we make an evolution of the system. To evolve the system, what we do is just to apply a sequence of stochastic maps. That is these operations here that are just transition matrices that have some properties that every element should be positive, definite, because these are probability transitions, see, and all the columns should sum equal to 1 to preserve the probability. Then this map transform my initial probability vector in a new one. Then we apply another transition matrix and we transform the, the remaining vector in a new one and so on. And we create some evolution of the system, right? Under this deterministically ruled or law. So then our quantum approach consists instead of using probability vectors, we should start with density matrices because we are going to introduce quantum effects. So for an initial state, a classical state, which is a probability vector, it's easy to translate it to a density matrix. Basically, it's a density matrix with all the diagonal, the elements of the vector probability. It's just that. This object here is a projector that projects to GTH configuration of the system. Now, the evolution of the system is created through these quantum dynamical maps. This sequence of quantum dynamical maps that transform this initial density matrix in a new one density matrix, and so on. Every dynamical map here should fulfill the condition that is completely positive and trace preserving, otherwise transform density matrices in another thing that is not physical. So this is necessary to preserve the properties of the density matrix. So for us, what we do is just to construct a representation of the crowds of every one of these dynamical maps. A crowd representation is a structure like this with these operators that transform our density matrix, and all of them should fulfill this identity decomposition. This is a guarantee that the dynamical map is a CPT schema. Yeah.
All the maps are the same in each time?
Not necessarily. Yeah. Here are distinguished by the N step or N application, but no, not the same. Not necessarily.
Is there in the classical case?
Also, not necessarily. Maybe in some Markov chains is the same, right? The same transition matrix, but not necessarily is the same. Okay, then to guarantee that this dynamical quantum version is a correspondence or is exactly related with the classical stochastic process, we need to apply this kind of definition. This object here is basically the classical stochastic map, the framework of open quantum systems, but do exactly the same like the transition matrix, only creates statistical mixtures, in the different elements of the probability vector. This object here it belongs to a set of incoherent maps. That means that cannot create nor preserve coherences in the system. So this object, on the contrary, of course, is a valid quantum map. Its objective is to create coherences, every possible quantum effect that is available. Then, when we apply this object to an initial density matrix, it's possible that the original classical state is transformed in an object that contains coherences or terms, interference term. Then we apply a projective measurement after this step, and the projective measurement destroy all the coherences and only left the diagonal of the density matrix intact. So if these conditions happen, means that this evolution, if I apply projective measurements in every elementary step, then I recover exactly the same stochastic process. And this is the idea. The idea is to analyze some classical stochastic process and introduce coherences such a way that if we apply kind of limit in the sense that we apply projective measurements that destroy every coherence created in every elementary step, we should reproduce exactly the same classical state. So there is some kind of correspondence, right? This is the general idea. What happens here? The dynamics in classical systems, these transition matrices create statistical mixtures, combine the elements every time that you apply the transition matrix to the probability vector, make mixtures of the different elements, right? So, in the contrary, when you apply the quantum dynamical maps, you don't.
This is like a Markovian process, right?
Yes.
How do you introduce memory in this type of?
We don't introduce memory because this is also a Markovian quantum process.
But how would you do it? How do you try it?
We don't try because in this sequence means that to be non-Markovian means that one of these elements should not be CPTP, right? And this is kind of.
No, I mean, the generic way to introduce non-Markovianity is that you let the step n depend on the previous steps, right? On the previous positions. So that would be meaning that, for instance, if you want a memory of one unit, of one time step, or two time steps, then you need, say, evolve a pair of probability vectors. If you want, right, and then this pair of probability vectors will depend on the one time step previous pair of probability vectors. Now you could do that for, say, 10 probability vectors, then you would have a memory of 10 time units. And still you would be able to write the same kind of process. But of course, it's not efficient. But in principle, that is how you could do it, and then you could apply the machinery as usual. Because otherwise, if it's not CPTP, then you don't really know. Right, then if you integrate out the curve, then you get the CPTP violation. But it doesn't make sense to construct the process on the basis of non-CPTP maps to start with. At least for me, it would be strange.
Yeah. Okay. Okay. Yeah. This is the thing. The stochastic transition matrix create statistical mixtures. Instead, the local dynamical maps create coherences. This is the idea behind our approach. The idea is in the blocks where the stochastic matrix creates statistical mixtures in the probability vector, we replace these statistical mixtures by superpositions of the possible states that participate in that block. So this is the purpose behind our approach. Okay. Now we should speak about the ANNI model. ANNI model is for axial nearest next nearest neighborhood of the Ising model. The classical description, I'm going to use this paper like a base to explain a little bit about how it works, but there is a lot of references about these kind of models and variants. The ANNI model consists in the following. This is the Hamiltonian, when we have a lattice of spins in one dimension, 2 or 3 dimensions. So there are two types of interactions. The interactions to first neighbors and the interaction to the second neighbors. Here in the Hamiltonian, I just put the parameter kappa, but usually a coupling factor here, J1, that tells you how much interact the one spin with its neighbors. And we have another J2, that tells you how much interact the spin with its neighbor, second neighbors. So, and more or less, this is what happened in, in a bidimensional system when you have different layers from the chains. And you have, for example, this spin interacts with its first neighbors through J1, the coupling factor, or J2 with the second neighbors, but also can interact with the neighbors with the different layers. No? And this is a vision for the for the three-dimensional system. Yes.
But in your Hamiltonian, the second term
Yes.
is J plus 1.
Okay, mistake. Should be 2 here, right? So thank you for the correction. Yes. Should be 2 here. Then typically what you do is just to factorize one J1, for example, and K is J2 over J1, the coupling factor. Okay, and in our case, we put J1 equal to 1. We only work in this kind of system, in one-dimensional system, and also in a finite system that is connected the initial spin with this with the last one. I mean, we have a ring, not an open chain, because obviously it's completely difficult in the quantum regime to work with many spins for the high dimensionality of the Hilbert space. Then we are going to work only with this, with a kind of ring. And yeah, okay, what kind of behavior you can find here in this kind? It's very rich in different regimes for the temperature and the parameter kappa, what is called the frustration of the system. For example, when this the system is at 0 temperature, we have different regions with different behaviors of the of the model. For example, for kappa less than 1/2, we have a ferromagnetic state of the otherwise the equilibrium state is a ferromagnetic state. It's basically all the spins pointing in the same direction, up or down. For example, these kind of things. When kappa is greater than 1/2, we have a different behavior of the system, and the system tries to reach the states with an antiphase behavior when you have a couple of the spins in one direction and a couple of spins in the contrary direction, something like this one. When you put kappa equal to 1/2, then the system is highly degenerate. You have a lot of the states. The system cannot reach one equilibrium state. So then this is the primary results that I try to reproduce in our system using our approach. And then I failed. I'm going to show you why, how. So, okay, what is our proposal for us? The idea is quite simple. This guy from here is our best quantum dynamical map that we have for the, we have a classical, this is the classical stochastic map. We create, based on this structure of this transition matrix, one local quantum map that creates coherences in the system instead of just statistical mixtures. And this is our best guess for the dynamics, for the quantum dynamics. And of course, this guided here is the same, but with the addition that in every elementary step, we apply measurements. So we destroy all the coherences in the systems. So we have a convex combination between the quantum and the classical. Of course, who is going to win in the dynamics depends on this probability P that for us is depending on time. So the big question is how we should propose that this P, depending not on time, on the temperature, should be proposed. The thing is this, in the transition matrix, when you introduce temperature, many elements start to be different from zero, or many blocks start to create new statistical mixtures that previously with zero temperature never happened. In our construction, these new statistical mixtures are transformed in quantum superpositions of the different blocks of the states. But this is counterintuitive because the temperature destroys the quantum effects, don't create more, right? So it has not much sense to put temperature to a system and see more quantum effects. Should be destroyed. Whatever is remain should be destroyed. For that reason, we propose that this probability that depends on the temperature, in this way, in this Boltzmann factor way, such a way when the temperature is very close to zero or zero, so this this expression goes to zero, and we kill the classical part, and we start only in the quantum regime, or our best chance of the quantum version. But when we increase the temperature, this probability starts to increase, and then this term is reduced, and we only have the classical evolution. So the idea is to analyze the system in small regimes for small temperatures very close to zero, to see if some quantum effects can survive, and if these quantum effects can help to the system to reach the equilibrium state or the equilibrium subspace. This is the principal idea. Okay, I'm going to put the figures in this way just to show you what is the... Sí. Ok, déjame ver si puedo. No veo mi curso.
Va a estar hasta la derecha.
A ver. ¿Se ve?
Sí, súbelo para arriba.
Súbelo hasta arriba.
Ahí. Oh, no.
Sí, ahora control más.
Si tienes la solo full plot y se ve.
¿Así?
Ya.
Ya se agrandó, pero...
¿Sí se ve?
Pero vemos la línea,
Se ve la
pero tienes
línea.
que explicar los colores.
Okay, very well. Okay, we are plotting here the probability to reach the equilibrium state. Remember that here in the different curves, we have in the first curve we have zero temperature and kappa equal to zero. This is equivalent to just the Ising model, right? Because the second interaction is not participating. So in this case, we know that that the final state of this of the system is the ferromagnetic state with all the spins up or down. So this curve corresponds to that. It starts in 0 and maximum 1. So tell us how the system, how it is evolving in time, is reaching the, the equilibrium state. Okay? This is the probability to reach the equilibrium state. And this is the elementary steps. Okay? The times that I apply the, the elementary operation. So in all these cases, kappa is equal to 0 and only change the temperature a little bit. So if you change the temperature a little bit, almost you will start in the same place, right? Temperature equal to 0.1 and 0.2, and all the curves are superposed. So of course, if I increment the temperature much more, this curve start to reduce to 0 because now the equilibrium subspace is not the ferromagnetic state. Then, okay, just to verify if the dynamics is doing the correct thing, right? Okay, let me just.
This is a zero temperature or zero
No,
temperature or more temperature?
it's for kappa equal to 0.
Yeah.
Are three curves. And temperature equal to 0, 0.1, and 0.2. And the curves are almost the same. Little. Also, this is just for 10 qubits because we are doing exactly the numerical simulation with the complete density matrix and the Krauss operators. It's not an approximation, it's exactly the. Okay. Okay, I'm going to do the contrary. I'm going to plot again three curves putting the temperature equal to 0, but changing the frustration parameter just a little bit, kappa equal to 0, 0.1 and 0.2 to see if some kind of the previous results as is explained in the paper that I showed you for kappa between taking values between 0 and 1/2, we should recover exactly the ferromagnetic state.
Before in this view, I don't understand the horizontal axis is the time.
Yeah, but it's not the real time.
No,
It's the time that is the number of elementary steps you apply to create evolution.
Your Y is like the
It's
time.
like time.
On the vertical axis.
And the probability to reach the equilibrium.
If for large time.
Yeah,
the
okay.
system reach-
Yes, I forgot to explain. At the beginning of the evolution, we prepare the system in a statistical mixture with the states with zero magnetization. I mean, the half of the spins point up and the half of the
This is
spin
my
point
question.
down.
What is the initial state and what is the equilibrium state?
The equilibrium is the ferromagnetic state with all the spins point up or down.
And the
So,
initial state?
yeah, the dynamics is basically is a disordered system at the beginning, and the dynamics start to order it in such a way that all the spins point up or all down at the end of the evolution. And this is the probability that this happens. No sé cómo quitar eso.
¿Vas a replatear algo en esta figura o?
No, y de hecho ya se va a terminar. No, debería quitarse.
Ahora es parte de tu computadora.
A ver, entonces.
¿Quieres que sea nuestra presentación?
No quiero poner la otra figura.
Es igual que se amontone hasta arriba. Y replot.
Ah, sí.
Oh, pero que se volvió a poner la otra.
Entonces cerraste a lo mejor la terminal equivocada y ya vale.
No.
A lo mejor es muy parecida.
O solo cambia con control shift. Al chip.
Alt Shift.
Sí, para cambiar la ventana.
No se cambió, no se ve nada. No.
Ah, bueno, ahora está.
O Alt. Arriba. La tecla arriba de shift.
Porque aparece la otra curva abajo, ¿no? O sea, la curva azul.
Ah,
Está.
no, pero ahorita se cambió algo. Ajá, ahí está.
Ah, okay. This is
Por
it.
debajo.
Yeah, okay. Again, I have three curves here. I'm plotting exactly the same, the probability to reach the equilibrium. Then the first curve is basically the IC model when the temperature is equal to 0 and kappa is equal to 0. Then I left the temperature in 0 and I start to change the frustration parameter. Just small changes, kappa equal to 0.1 and 0.2. The curves for the kappa equal to 0.1 and 0.2 are superposed here. You cannot see very well, but appear here. That means that even for small values of the parameter kappa, the system gets freezes in some point that doesn't allow to the dynamics to help the system to reach the equilibrium. And this is kind of weird because if we saw that, okay, in the paper that I showed you, in the behavior of the system when the temperature is equal to 0, for values of kappa between 0 and half 1, the system also should reach the ferromagnetic state, but this doesn't happen here anymore. And I spent a lot of time trying to correct the program to see what is the problem, but it's not any problem. This is the behavior of the Glauber dynamics that we apply here. It's not possible for the Glauber dynamics to make the system to reach the equilibrium for different values for kappa, even if they are very, very, very small. The explanation is something like that, because, for example, if you have one configuration like, I'm going to put two and you want to transform in one configuration like this one, for example, the idea is that the big domain increase and we reach the ferromagnetic state at the end. We need to change spin by spin down, right? So when I apply the rule, the dynamical rule here, the delta, the difference of the energy between the final state and the initial state is equal to 4 kappa. Then in the Glauber dynamics, when you put the temperature equal to 0, the rule is that if delta E is less than 0, you preserve the flip of the spin. You maintain, or you do the flip. But if the delta E is greater than 0, you reject the flip of the spin and you recover the original configuration. But if delta E is equal to 0, you put the spin with half of probabilities up, half probabilities down. This is the rule that we follow when the temperature is equal to 0. But when the temperature is different from 0, we cannot apply this anymore. So if the kappa is, even for temperature is equal to 0, if kappa is different from 0, we have delta E greater than 0, right? Then we reject the flip, and then the system remains freezed, can never get to the to the ferromagnetic state. So the
This is pure classical.
pure classic. No, this is quantum dynamics. I didn't show you the quantum effects there. Then the hope is that we can. What happens if we introduce the small values of the kappa parameter, but also introduce small values of the temperature? There should be some kind of
with quantum, the quantum version, zero temperature.
Yes, it's for the Hadamard version of the dynamics.
Quantum.
Yes, the quantum effects doesn't help in this case. Okay, I can try to show you the last figure, which is the one where,
And Gustavo,
yeah.
could you please show the? Do you have the coherence for this one? Could you please show that?
Yeah, I mean I can, but the problem is the computer doesn't want to show. Yeah, but it's also the time.
Yeah, time is also.
So okay, the idea is that if I've introduced small values of the temperature for the different values of kappa, we saw that these curves start to increase, right? So the temperature, when it's very small, helps to the system to reach the equilibrium state because the temperature excites the system in such a way that push out the system from the local minima and try to reach the global minima. So this is the idea. I'm not going to show the last figure, but this is basically what is happening. I start to introduce temperature different from 0, these curves start to increase. It's like not too much, but we need to see how much temperature is useful to help to the system to reach the equilibrium. And yeah, that's it. This is the preliminary results that we have for this. That eventually, when we manipulate the different parameters, temperature and kappa, the quantum effects that survive can help to the system to reach the equilibrium faster. This is our hope, but we don't know if this will happen in this kind of mode for now. Yeah, that's it. Thank you very much. Some doubts, questions?
Maybe a comment about the temperature, right? Because I think one has to, maybe possibly one should keep these things apart. So so if you assume that you have a system at high temperature and that the system is classical due to the high temperature, and you looking for quantum extensions, then this is a contradiction by itself somehow. Right? Because at the end you want to describe your system because so you have your classical system at high temperature. So you say, okay, I will do my quantum extension. Then this is more quantum than expected, but you must assume that it operates at a low temperature. Of course, in your systems, you mentioned you're not really interested in the low temperature behavior of the system because the systems are optimized for working at high temperature. So if you're looking for quantum extensions, it's not really a quantum extension of high temperature dynamics. So it should be quantum extension of some classical dynamics, which might very well be zero temperature dynamics, where you then introduce, say, temperature as an additional ingredient and check if quantum features survive.
We are doing at small temperature.
Yeah,
Yeah,
but that's
of course,
not
if I
because you want
increase the
to go
temperature
at high temperature.
higher, of course, the system also never reached the equilibrium state.
No, we are, when we are increasing the temperature, we are increasing the temperature very low. And it, as it is one dimension, and in one dimension, you know, for the case of the ANNNI model, for the Ising model, you know that the temperature actually is giving us more temperature, it diverges. That's why the ANNNI model is better option. Now, ANNNI model, you have a critical temperature where it will not diverge your noises, but we will play below that temperature. So we are really looking at the low temperature.
But do you have randomness at zero temperature?
We start with a random condition, that's true.
No, in the process, not in the initial condition.
I don't understand the question.
I mean, because of this kappa, do you have really situations where you have to choose
Yes.
at random?
At zero temperature, you have randomness also.
At zero temperature?
Yes, you have randomness also.
So, I mean, my idea would be to look for quantum extensions of this zero temperature dynamics and then see what happens.
Yes, that's
if
exactly what he is showing in this picture.
This quantum extension does at non-zero temperature.
Yeah, so our quantum extension, this is the figure he is showing there. Our quantum extensions, that one, okay, do not take you out of the freezing at zero temperature.
Yeah, that's, I mean, this is a possible result, but I think this is the right way to do it. Yes.
He said that's exactly the figure he is showing.
Yeah, okay.
Now, one approach could be to see that if there exists, because now we have a series of quantum extensions, group of quantum extensions, if there exists a quantum extension which will take it out of the freezing.
Yeah.
That could be one approach. But given that Hadamard and SYH is the most efficient one, I don't know.
Are there more questions? Okay. Well then, thanks again. And we come to the next talk by